Welcome back. Now we're going to look at graphs in detail, because just doing the basic shapes doesn't always make sense for us. Okay, so we're going to do a little bit of a case study. So what we're going to do is we're going to consider a small ball that's projected upwards. In other words, I've got a ball and I'm throwing it, okay? And I know for some of you that you don't like this whole thing because you go, what about when the ball's in your hand? We're considering, yes, my hand has to exert a force on the ball, but I'm looking at when the ball leaves my hand, okay? Then my hand's no longer part of the issue, and it's moving just under the force of gravity, okay? So that's what we're looking at. So we have a small ball that we're going to project upwards, and I'm telling you that I'm throwing it upwards at 19.6 meters per second. So that is my initial velocity. That's not going to change. That's going to be the velocity for this whole, the initial velocity for all of it. So I am now going to want to draw a velocity time graph. What I have here is a whole bunch of times. We want an accurate graph, so I need to know what the velocity of the object is. We're going to take up as positive, okay? We're going to use that the whole way through, which means for me that acceleration is minus 9.8. That's important because the object's going up, acceleration comes down, so that means as it goes up, it's going to slow down, and maybe somewhere along the line it's going to stop, and then it's going to come back down, okay? I am not assuming for all of this that it's just going up the whole time. I'm going to have to see. Right, initial velocity was 19.6. I need to calculate the velocities for all the rest. Thinking about the information I have, I'm going to use this equation. Whoops. If I write it correctly, that's always important. VF equals VI plus A delta T. Now what's going to stay the same is the fact that that's 19.6. This is minus 9.8. And for each of these equations, I'm going to change time. First one is at 0.5. Right, so we need to have our calculators. Let's just put that here quickly. So we've got 19.6 plus, and it's going to be minus 9.8 times 0.5. And remember, we can't work with it as a fraction, so we get 14.7. So I'm just going to put that in there, all right? Now, what we're going to do is instead of a half, this becomes 1. Okay, so if you look carefully on your calculator, the really nice thing is we can just go back there and I'm going to put a 1 in instead. And now we get 9.8. So it's quite a big change compared to the first one. I'm going to do the same thing now. And instead of that, I'm going to put 1.5. And I know this feels quite tedious and laborious, but it's actually quite important. So we're going to go back there. I'm going to make that 1.5. Oops, no, I don't need that second bracket. There we go. We now have, oops, that's what I want, 4.9. So we're starting to see in 1.5 seconds it's changed quite a bit. We need to go back here. Instead of 1.5, we now have 2. Go back to our calculator, and we're going to change that to a 2. Oh, 0. So after 2 seconds, it's reached the top of its motion. Okay? Now we need to look at what happens after that. So our assumption is that now it's going to come back down. Up was my positive direction. So it means that now I should be getting negative velocities, okay? So let's see if that's what happens. So again, we're going to go here. We're going to change that to 2.5. Let's go to our calculator. 2.5. Oh, look, minus 4,9. I'm hoping some of you can see what the trend here is going to be. If I now take this and make it 3, there we go. I'm hoping some of you can take a guess as to what my new value is going to be. Ooh, minus 9,8. Are you starting to see what's happening with these values as I go down? That there's some sort of symmetry, and that's good. It's what we want. Then we need to do 3.5. There we go. So we put this into our calculators again. Okay, close my bracket. Oh, look, 14,7. So what do we think is the very final velocity going to be? If we look at the trends, okay, it went 19,6, 14,7, 9,8, 4,9, 0. Then it started again, minus 4,9, minus 9,8, minus 14,7. So I'm going to make a prediction, and I think that this final one is going to be minus 19,6. Let's just check, though, because you never know. So over here, we're going to put 4. Let's check. Let's get rid of that. Times by 4. Oh, look there. 19,6. I'm happy with that, because by now you've been told that the velocity I throw it up with is the velocity I'm going to catch it with, as long as it's at the same place. Okay? That's the important part. We're now going to take this and put it onto a graph. So we're going to draw an accurate graph. So here we go. I probably haven't made my graph long enough, but it's all right. There's delta t. There's v. Now, for me to do it completely accurate is a little difficult on the board because I don't have a ruler. You really do need to practice doing this properly. So we had time frames that were 0.5, 1, 1.5, 2, 2.5, 3, 3.5, 4. Okay? Now, if we go back to our values, they're changing by 4,9 every time. So this is a graph where I can use 4,9 as my scale. But we wouldn't normally do that. We'd go 5, 10, 15, etc. But this one, because if you go and minus, so this is a little bit of a trick here, if I minus those two together, I'm going to get 4,9. If I minus those, it's 4,9. Minus those, it's 4,9. So the velocity is changing by 4,9 every time, okay? And we're okay with that because it's half a second. That means when I get to my graph, I can go, oopsie, 4,9, 9,8, 14,7, 19,6. Minus 4,9, minus 9,8, minus 14,7, there's a minus there, and minus 19,6. Okay, I've got all my points. Don't forget your 0. This is an accurate graph, so you would plot it nicely. So you would go, we're starting at 0. My time was 0, so there's my, whoopsie, there's my first point. At half a second, it was there. At 1 second, it was there. At 0. Okay, this graph is very not accurate because you can see it's already going to become a little bit of a curve because my spaces aren't the same. But you get the idea of what we want to do. And what we're going to get is this. So let's get rid of those really bad marks because they're not working so well. Okay, and my graph, and went past there and down to here, and at 4 seconds, it was here. It's a straight line, and I know for some of you, you're going, but it changed direction. Why did it keep going down? Because it changed direction. Okay, yes, it was speeding up. Negative is a direction. Negative here doesn't mean slowing down. Negative means I've changed direction, but you can see the velocity gets bigger and bigger and bigger. Okay? So on this graph, what I can see is that my object went up, stopped, came back down. I chose up as positive. So this graph gives me a nice idea. It's a nice straight line. I'm always going to get straight lines. The gradient of this graph must give me the acceleration of my object. And the area under the graph tells me how far it's gone. So when we look at this and we go this area, and it's a triangle, remember that's a half base times height, gives me the distance. If I want the total displacement, I have to add it to this area. But that area is negative, and the two will cancel out. Gradient, which gives me the acceleration, is the change in the y value, which is v, divided by the change in the time value. Please be careful with these ones, because what happens here is, say I use a point that's 0, you don't show the 0 in your calculation, and then you run into trouble. If you're working out a gradient, I must have 2 points. Even if one of them's the origin, I still need to include it in my calculation because I'm working out a gradient. It's a change in. So I have to show the two things I'm comparing or changing in from, okay? Now, let's look at the position time graph. So again, I'm taking up as positive. I can't change my sign convention, okay? You just can't. So we're now realizing that we're going to use VF equals VI. Oh, no, we're not using that one. Again, apparently my brain has gone on strike. So we're going to use delta Y equals VI delta T plus a half a delta T squared, okay? And we would do exactly the same thing as we did last time. Now, first of all, position when it's 0 is 0. It hasn't moved, okay? What will happen here is we're going to go, no, we're not. Apparently it doesn't like me. So 19,6 times 0,5 plus a half minus 9,8, 0,5 squared. I'll stretch, okay? So we put this into the calculator just quickly because I want you to see it. We're going to... Okay, so we've got 19.6 times 0.5 minus 0.5 times 9.8, oopsie, not 98, times 0.5 squared, oopsie, maybe I should put a 5 there, so what happens when you're in a hurry. And we get 8,57. Now, I'm about to run out of time, which is not a good thing, so you would need to do all of this, okay? When you plot this graph, and you'll do it accurately for me, you're going to see this. None of your positions are going to be negative. You're only going to get positive answers. They're going to get bigger and bigger and bigger, then they're going to get smaller and smaller and smaller till they get to 0 again. It doesn't go below the line because I didn't change direction. Well, I did change direction, but I didn't go below where I started. Okay? And now, so we get a nice curve, okay? So I'm going to leave that to you. You need to just work through that. It's important to do these accurate graphs. The nicest thing about this is I chose up as positive, so I don't actually have to work out my acceleration because it's constant. So my acceleration graph will be drawn at minus 9,8. There we go. It'll just go across and end at 4 seconds. That's all it is. Acceleration due to gravity can't change direction, okay? So we've got this nice graph, nice and straight, and if I had to calculate the gradient of my velocity time graph, that's the value I would get. That's where we're going to end it for now. We're going to take a short break, and I'll see you in a couple of minutes.